Shachar will tell us about the Fourier spectrum of polynomials over finite.
Okay. So that's really the part I didn't speak about in my last talk. But I won't assume anything from the previous talk, so I'm just going to start from scratch. And what I want to show you is just one result. It says some property of Fourier coefficients of polynomials over finite fields. And essentially what it says is that you can always find a small set of variables such that most of the Fourier coefficients contain at least one of these variables. So one example to think about where this doesn't happen is, let's say, the majority function, right? The majority function have all these Fourier coefficients kind of spread around. So polynomials do not behave like the majority function. That's one, at least for me, it's a nice quantitative way to think about it. So let's just start by describing the result. So I will be studying polynomials over F2, but that's just for simplicity of notation. There's nothing special about F2, and everything generalizes to any finite field just automatically. So you don't really have to do anything. I'll tell you which parameters change. That's the function. And so the Fourier coefficients are just the usual thing. It's a correlation of our function with linear functions. So it just will be something like, so I'll denote it the alpha Fourier coefficient of f. It's really the alpha Fourier coefficient of -1 to f, but let's denote it like that. That's just the average over a uniform input of the correlation. Can you see it here, or is it too dark? Between f of x and the linear function x alpha. Okay, so that's just the usual Fourier coefficients. And, well, obviously we know from Parseval that the sum of the squared of the Fourier coefficients is 1. So they, in fact, the squares they define this natural distribution of Fourier coefficients. And now this distribution, most of the Fourier coefficients will contain this variable for the small set. So that's, where should I write it? Okay. Let's do it this way. So what is the theorem that we'll see today? So let f of x1, xn be a degree d polynomial. Then you can find always a set S of variables, and this set is quite small. It's something like order, okay, there's also a parameter you choose, so you choose some epsilon, should be some error parameter they can choose. So this, you can also have a small set of variables, something like 1 over epsilon to the 4 to the d, such that if you look on the sum of the squares of all the Fourier coefficients which do not intersect the set S, so let's say it's alpha restricted to the set S is 0. So all the Fourier coefficients that do not contain any variable from the set S. And also we'll have to exclude the 0 Fourier coefficient just because the polynomial might be biased. So, and also alpha is not the all 0 Fourier coefficient. This sum is at most epsilon. No. Sorry, alpha is not 0. Good. Alpha is not 0. So if we sum over all these Fourier coefficients, we'll get at most epsilon fraction of the mass. So that's the theorem that I'll show today. And I just want to say that if you have a general field, so in Fp, then essentially what you get is that the size of S is something like p over epsilon to the 4 to the d, or maybe some constant here, order of it. So if p is some small constant, and really what this tells you is that you can't, then you can't really hope to optimize by choosing the epsilon to be large, right? So essentially you only start getting for epsilon, which is roughly 1 over, when epsilon is smaller than 1 over p, then those two things are roughly the same up to some polynomial factors. So you might hope that when the field is very large and you can satisfy yourself with a constant error, let's say, you might do better. And it might be possible. So we never try to optimize it for very large fields. But if the field is small, then that's what you get.
You mean, so how close is this 4 to the epsilon to the 4 to the d estimate for F2 even?
So for F2, oh, you mean what is this tight?
Yeah, how tight? Or
So
how
it's not tight at all.
what should be the truth?
So
Let's say even for F2.
So let's say, so for d equal 1, I'll show you the size is 1. So if d is 1, just a linear function, so you just have just a single Fourier coefficient, which is not 0, and its value is 1. Choose any variable in this, and it will be, and you will kill all the Fourier coefficients. If it's a quadratic polynomial, it's not hard. I won't show it here, but it's not hard to see because we really understand the Fourier spectrum. You can just choose a set to be of size log 1 over epsilon. So I don't know what happens beyond d equal 2, maybe logarithmic, maybe pre-logarithmic, but we don't have any counterexamples.
Okay. At least it grows with a degree.
So from 1 to 2 it grows.
Okay.
At least, yeah.
Okay.
Okay, good. So that's a theorem that we'll see. Okay, yeah, let's hide it. Good. Maybe I'll copy the theorem here. So wait, which side is better, the right or the left? Right. Okay. I just copy the theorem here, so we'll remember it. So f is a degree d polynomial. We have some epsilon, and there exists a set S of variables. Its size order 1 over epsilon to the 4 to the d, and the sum the square most epsilon, where we sum over all the Fourier coefficients, which are 0 on S, but which are not the 0 Fourier coefficient. So I won't delete it, it will always be here. Okay, so before proving it, I want to just show you an equivalent way that will be useful in viewing it. And that's a way by looking at some derandomization of choosing independent elements to a polynomial, independent inputs. So I want to define this distribution which we call d of s, so it will be a distribution over f2 to the n times f2 to the n, a distribution over pairs of inputs to the polynomial, and it will just be, so how do you do it? Well, you just choose x and x plus y, where x is a uniform input, and y comes from just choosing elements in this small set S. So that's a pair. So an equivalent way of looking at this distribution is we're choosing the first element uniformly, and then for the second element, we take the first element, we copy it, and you just resample the element inside the set S. Okay? That's an equivalent way. And actually, so you can write this formula. So let's call this quantity that we're trying to bound this delta S of f. That's a quantity we want to bound. So here's a claim which I won't show, but just simple Fourier analysis, is that you can also write this delta S of f in the following way. So you take x1, x2 coming from distribution ds, so they're coupled inputs, and you look on the correlation between f of x1 and f of x2, and we subtract it from the correlation if we just choose them uniformly and independently. Okay. So what do we have here? So we're looking here, so we're choosing two independent inputs. Here we're asking, here this is exactly, essentially what is the average of -1 to the f, or the bias of f squared. Right? So it's a correlation you get between two uniform inputs. here is something that says what is the correlation between two dependent inputs. And now this is just equation just followed by just simple Fourier analysis. But what it tells you is that, well, if you believe the theorem, then you can choose, if you want to choose two independent inputs to your polynomial, you might as well choose them in some dependent way. You choose the first one uniformly, the second one you just re-randomize a small number of elements. Okay. And then the last thing I want to talk about before I start the proof is that, well, here we're just asking what happens if we have a single polynomial and we want to choose two inputs for it. You might want to choose, you have two polynomials, you want to choose one input for the first polynomial and then a second input for the second polynomial. So I want to argue that it just follows from the same things. So let's define a similar notion. So we'll define it, so it will be delta S of f and g. So now you have two polynomials. And I'll use this definition there, but you can also use this definition. They're the same. Just the sum of all the Fourier coefficients. Alpha S is 0, alpha is not 0, of f at alpha g hat alpha. So if you want to choose, so an equivalent way would be to choose the correlation between f and g over dependent minus independent inputs. Now, assuming you want to bound that, well, actually, it's enough just to bound either f or g. So here's just a simple claim. Delta S fg is at most a square root of delta SF delta SG. So first, why the claim is true is just by Cauchy-Schwarz. Right? So you just look on that. You do is the sum of squares of that is delta S of f. The sum of squares of that is delta S of g. So that's just Cauchy-Schwarz. But conceptually, it tells us that it's enough to find a good set for one polynomial in order to bound its correlation with any other polynomial, any other function, in fact. Okay. And this, in fact, will be useful in the proof. Okay, so now I'll start talking about the proof, and the proof will actually... So first I want to tell you what doesn't work before starting to show the proof. So you might hope that, well, let's choose the set S randomly and it will work, right? So it might... So I want to convince you that it doesn't work. So let's do it. What doesn't work? So we said what doesn't work is choose S randomly. Exactly. So as Noga said, maybe your function just some function of a square root and number of the variables, right? So then it may be a very complicated, a very nasty polynomial, have no specific structure, but it just depends on a small number of variables. So you can't really hope to say choose S randomly. So even if your function has very small Gauss norm, it's very pseudo-random, whatever, you can't hope to do it. And then you say, okay, but maybe this doesn't depend on all the variables. What if you choose a random set that of the variables on which the polynomial depends? So you might hope to, so here's another example. Choose, let's say, f of x1 to x square root n times g of the remaining variable. Right, so now this depends on all variables, but you need to choose at least one variable from here. Okay. Well, but this polynomial now has structure, right? For example, its distribution is biased. It can be approximated by a degree polynomial. So you might want to say, well, what if my polynomial depends on all variables and it doesn't have this structure? Then it may be true, but we don't know how to show it. So our proof goes through a different approach. So we won't choose the set S randomly. We choose it carefully, somehow dependent on the polynomial. So I'll also copy this distribution ds here. So we also need it. Ds will just be this distribution of x plus y. Well, x is in f2 to the n, and y is in f2 to the s. So I think we have all the theorem and some definitions here, so okay. So actually the proof will analyze things, does your function look like a random function or not, but the analysis will not be by choosing S uniformly. So we'll have two lemmas and they will tell the proof. So lemma 1 will say what happens if f has some large Fourier coefficient. So if the maximal Fourier coefficient of f is, let's say, above epsilon, so epsilon is a parameter that we want to, the error that we want to get, then, well, okay, maybe I'll just add a bit more notation. So,
do you want that squared?
No, epsilon. Yeah. Well, it's maybe a parameter you can optimize, though, but for this talk to say epsilon, but the right parameter will be some polynomial in epsilon, maybe epsilon squared, I'm not sure. So let me just do a bit of notation. So we say, so let's S f epsilon be this set for f with error epsilon. So it's just this set this theorem guarantees, and let's call C D epsilon just be the maximal size of the set S f epsilon for the greedy f. So this is just a way of saying, well, we want to prove some bound on the size of the set S. That's what we'll try to get at the end, 1 over epsilon to the 4 to the d. And for now, let's see we don't know the answer. So let's say CD of epsilon be this number we want to get at the end.
So if S of f epsilon will be the smallest set?
Yeah, the smallest set S that attains these bounds. So this is just a way of writing those lemmas. So if f, so f is a degree d polynomial, let's say, put it here. So yeah, f is a degree d. F has degree d. Then so just between two inductive claims. Then, well, the size of the set f epsilon is at most what you'll get for d minus 1 polynomials with error roughly epsilon to the 4 and 1 over epsilon to some order of 1. Here's also some constant. So what does it tell us? Well, if you want to bound, this is just an inductive argument, right? It says, assume your function has some nice structure, it can be approximated by some linear function, then you can find this set somehow by going inductively to lower degree polynomials, right? So, and then the other lemma, say, well, what if you don't have any structure? If your maximal for equation is at most epsilon, well, then essentially what you get is the same, but by different methods. Say order of epsilon squared, 1 over epsilon, some constant. So we'll have two cases, one where f is structured, can be approximated by linear functions. The other one where f is pseudorandom, doesn't have any large Fourier coefficients. And in both cases, we'll be able to induct to lower degree polynomials.
Yeah. Isn't it clear that S should be the set of the most influential coordinates? I mean, why even?
So for example, maybe all the coefficients have the same influence, more or less, right? So take a random polynomial, okay? So all the variables have very, very small influence. Anyway, no, actually they'll have noticeable correlation, but it might be that many of them have large or more or less the same influence.
I mean, but you can.
There might be.
You can, for a majority, you can't do. Anyways, you can't approximate it with a small set, as you said in the beginning, right?
Yes.
All I'm saying is that you have no motivation of inserting to S low influential coordinates, right? That's clear.
Yeah, well, I'm not sure, actually, because that's not the way we prove it, but take the product of a polynomial of, let's say, square root n variables and polynomial on the remaining variables. then the variable here and the variable here would have roughly the same influence. Something like 2 to the minus d, more or less. So they have roughly the same influence, but still need to choose one from the small set. There might be, maybe if you look very, very delicately on the influences, maybe there's something we can do. We don't know how to do it. So we don't analyze it by influences. But maybe there's a way of doing it.
That's the way Friedgott's theorem was proved.
Yes. Yeah, but somehow here we couldn't analyze it via influences. So, but I'll tell you what does work. So I just want to give you some intuition about the lemma, then we'll start go into proving them. So the first lemma is slightly more standard. Essentially what it tells us is that if your function has some large Fourier coefficients, it can be approximated very well by lower degree polynomials, which somehow be related to its derivatives. So I'll define derivatives in a second. So we will say that we can approximate the function very well, and it will be good enough somehow that you'll take the derivatives, it will approximate the function, you build this set for each derivative, and you combine them together. So that will be the way we show the first lemma. The second lemma, somehow you want to utilize the fact that you don't have any structure, and what we'll see is something that's somewhat bizarre. We'll show that if you choose a vector space that has nothing to do with your function, and you look on all derivatives on a vector space, they approximate this quantity that you want to bound, this delta S of f. And somehow by choosing this random space uniformly, so it will give you a bound on that property that you want to bound by choosing any vector space. But then you need some property of derivatives on vector spaces, and somehow by choosing this vector space uniformly, you can bound it by the. You can show that if you have no large Fourier coefficients, then a random vector space will be nice. So let me just start with the first lemma. Okay, so first, our lemma is clear. So we have two scenarios. Either we have a large Fourier coefficient or we don't have. And in both cases, we'll induct to lower degrees. So actually, a convenient way of inducting to lower degrees that we use quite a bit for polynomials is just taking derivatives. So it's a natural way of getting from a degree d polynomial to a degree d minus 1 polynomial. So I want to define derivatives. So derivatives, so those will be directional derivatives, because we're working in some finite space. So let y be some direction, f2 to the n, and we define the derivative of f in direction y just to be f of x plus y minus f of x. So that's the definition of a discrete derivative. I'm sure most of you have seen it. And one nice property is that, well, if the degree of f is d, then the degree of any derivative is at most d minus 1. And so it has the properties that we want. And one way to see it is just think of y as constants and x's as variables, and just expand all the terms. And if you open all the brackets, then all the terms that depend just on x will cancel on both sides. So all you get left is these mixed terms in x's and y's, and those must have lower degree in x. That's an easy way of seeing it. So we'll use derivatives. So I want to start with the proof of the first lemma. And for the first lemma, there'll be this claim which essentially will more or less show why it works. So it says, so assume that f has some large Fourier coefficient, then, well, you can find a small number of low degree polynomials, where k will be some small parameter, and the degree of gi. So I assume throughout from now on that f is a degree d polynomial. So the degree of gi is at most d minus 1, and they approximate f. So in which way they approximate f? So let's even say this is equal epsilon, just to make our life easier with notation. So you can just write the function look at the function minus 1 f of x, and we look on the average, the following average. So I want to say this is small. So in this case, what we need to be small in the L2 norm, so let's say the average over x of that squared is at most, let's say, epsilon squared. But you can take almost any type of approximation that you need. So I'll prove that in a second. But intuitively, what it tells us that if you have any degree D polynomial and it has some Fourier, some large Fourier coefficient, then you can just find a small number of lower degree polynomial that approximates such that their average, or if you didn't have this epsilon, it just be the average of -1 to those polynomials. So you need some coefficient here that depends on the maximal Fourier coefficient, and this average approximates your function very well. And you can choose almost any type of approximation that you need. Okay, so let me show it. So if I write on the left board, can you see it? Let's try and see. So let's try and prove this claim. So the point is that first we just want to go from some function which has some large Fourier coefficient to a function that has a large zero coefficient, or it has bias. So let's say h of x be f of x, and let's say we remove the maximal Fourier coefficient, so such that just the average of -1 h of x is, let's say, epsilon. Okay, maybe if here this was if this was minus epsilon, then we need to add a constant there. So, but it doesn't matter. So this is just a shift of the function so that we can just have a large bias. So now here's another claim that I'll show you in a second. You can, well, for every x, you can write this function.
Alpha is the large Fourier coefficient?
Yeah, alpha is the large Fourier. Alpha, this is a maximal Fourier.
Oh, and everywhere you mean alpha could also be 0, right?
Alpha, I don't care. I just want to shift it so it will be, you have a large zero Fourier coefficient.
Probably also D needs to be at least 2 for this.
And D needs to be at least 2 for that, sure. Yeah, but for D equal 1, it's easy. Yeah. Good. Good. So I just want to claim that this is just, you can just always write it as the following way: 1 over epsilon, go over random derivatives, and look on this function, on the derivative. So that's a two-line proof. I'll show it in a second. But essentially what it tells you is that if you take any function that is biased, you can always compute it exactly as an average of derivatives. So once you have that, then getting this approximation is very easy. You just choose a small number of them and use some Chernoff arguments and get approximation that's good in almost any way you want, right? So I want to do the calculation, and then okay, that's some function derivatives of h. Those are the function that approximate the function h. But if you add back this linear term, you get those functions which approximate f. So I don't want to do this. It's just a simple calculation. There's nothing new here. And if you haven't seen this before, then it's actually quite nice. So I want to say that for every x, you can write any function which has a constant bias by average of derivatives. So what's the proof of that? Well, let's just multiply those two things. So this is a constant, doesn't depend on y. So what do we have? So we're looking on the average over y of the -1 of h of x, let's say plus h of x, hy of x. So since we're over f2, I don't have to care about signs. That's actually a minus, but doesn't matter. So we have that, right? That's multiplying the two sides. So what is h of y of x? Remember, this is just h of x plus y minus h of x. Just difference. So those two h of x's cancel out. And this term, so x is some fixed number, but y is uniform. So x plus y is uniform, so that's a uniform element. So this is just epsilon. So that's the entire proof. Okay, so essentially, what this claim tells us? Well, if your function has some large Fourier coefficient, in fact, this will also work if it can be approximated by any low-degree polynomial. You just shift by this low-degree polynomial instead of shifting by this maximal Fourier coefficient. So you can always approximate it very well by an average of low-degree polynomials. Yeah.
There you could have taken an exact equality. So the reason you took approximation was that you wanted k to be small.
Yes, I want k to be small. So if you want to get, so k here will be something like 1 over epsilon to the order of 1. So that's the reason. Because now what we'll do is for each one of those functions, we'll just choose a set S inductively, take the union of those sets, and then argue that this union of these sets is a good set for F. So that's why we want K to be small. Okay? So let's do it here. Okay, so what do you say? So now we have this claim, and just set S for F to just be the union of those sets S for GI, for I going from 1 to K. Okay, so maybe that's not clear. So I think, so let's say it's a set for F with parameter arrow epsilon. Maybe here we need to choose something like epsilon squared or to the 4. Or let's see. Yes, so epsilon to the 4th. So for each one of those sets G, for each one of those polynomials G, we'll choose inductively a set with a somewhat smaller error. Takes the union of those sets, and now I want to argue that this set is good for F. So maybe I'll just try to do it a set of S, and then the claim will be that delta S of F is at most epsilon. So the proof is, again, there's nothing fancy here, so I'll just do it quickly. I really want to talk about the second lemma, because there we have a new ingredient. So what's the proof? So, well, you just have to check it. So define this function capital F of X just to be this average that we have here. This average that approximates -1 of F very well. So just to be 1 over epsilon K, sum I from 1 to K of -1 of GI of X. And we want to bound that, so let's write it in a different way. Where should I put it? So now just to check, so let's see, what is delta S of F? Well, it's just the sum over all the Fourier coefficients, which are 0 on S and not entirely 0. So it's just the sum of the squares of the Fourier coefficient F. So let's just, one of those, I'll break by capital F, so it'll just be, let's say, F hat alpha, and here I'll put minus F hat alpha. F hat alpha plus the sum of all the same things over alpha, F at alpha. Okay, so we just break it in two terms. We just show that this one will be small just because the function capital F approximates the function -1 to the small f very well. Okay, just because we chose this approximation, it tells us that L2 approximation is the right approximation to choose. This will show that the first term is very small, and this will be very small just because each set S for polynomial GI was good for it. So let's just see why it works. So let's bound each one of those individually. So let's start with that. So what do we have here? Well, we can always bound it by Cauchy-Schwarz, by the sum of the squares of that times the sum of the squares of that, and then taking the square root. Right? And the sum of the squares of this polynomial is always 1. It's actually below 1 because we don't sum in over all the Fourier coefficients, or only some of them. So that's at most square root of the sum of f hat alpha minus f hat alpha squared. Okay, that's just Cauchy-Schwarz. And here, let's say I'm even summing over all the Fourier coefficients, not just, so let's say even a larger bound, summing over all the Fourier coefficients, not just those in the small set. Now, this is just the L2 norm of the Fourier spectrum, which is the same as the L2 norm of the functions originally. So that's just, actually, this is just that. The same thing. That's just, I don't know how to write it simply. That's just the, so it again will be square root of the average over x of minus 1 f of x minus f of x squared. So this is just because we chose a good enough approximation. And this is at most epsilon. That's the way we chose the approximation. Okay, that's the first part. This just says the function capital F, this average, approximates our function well enough. So what about the second term? So let's just expand. So what is capital F? So just 1 over epsilon k. And what do we have here? The sum from I from 1 to k. Now we have this mixed term, right? So we're summing over the Fourier coefficients, all these Fourier coefficients. Well, one time for the function g, gi, multiplied by the Fourier coefficient for the function small f. So just this mixed term that we call delta s of gi f. This is just a correlation between gi and f. So let's just repeat it again. Maybe it's not clear. So it's just equal to that. So again, capital F was just this average. So 1 over epsilon k comes down, and we sum over all those functions. And for each one, we're looking on the alpha Fourier coefficient of it times the alpha Fourier coefficient of small f. And we're summing over all the Fourier coefficients, which are of this specific form. There are 0 on S, except for the 0 Fourier coefficient. So that's exactly the type of Fourier coefficient that we're looking at. So we get this mixed term. And as we already said in the beginning, it's enough to bound one polynomial to bound the correlation of it with any function, in particular with small f. So that is at most, again, by choosing the parameters right, it will be at most epsilon. Okay? So that finishes the proof of the first lemma, which says if a function have large Fourier coefficient, then we can prove this theorem, and the proof went by, we just approximate the function as a function very well by low degree polynomials, and then just for each one of them, find a small set, takes the union of the sets, it will be a set for the original polynomial.
But somehow you had there epsilon to the 4.
Yeah, so you need to optimize. If you optimize the parameters, then you get epsilon to the 4th. You're asking why epsilon to the 4th? Essentially because you have here, this is bounded by the delta for g.
Yeah, but not for k. What you wanted is to get the delta sd minus 1 for epsilon to the 4.
Yes. So you're asking why? Why epsilon to the 4th? Okay, so this is bounded by square root of delta s of g, right? So that's epsilon squared, and this has to kill this 1 over epsilon here.
Okay.
So you need epsilon to the 4th. Okay. Okay. So now I want to talk about what I think is a more interesting part, is that how can you argue about a function which has no structure? In this case, it have no large Fourier coefficients. So let's assume that f has no large Fourier coefficients. So the maximal Fourier coefficient of f is at most epsilon. So here's a claim, which will be some of the key claim. So let V be a vector space, any vector space, then we can bound the quantity that we want for f by the following thing. We're going to run over all the elements in this vector space, take takes the same quantity that you want to bound for the derivative, and then also add back somehow the 0 Fourier coefficient of it. Good. So let me try and explain what's going on here. So for me, it's somewhat mysterious. So somehow, and I'll show it in a second, if we choose our derivatives to come from a vector space, from a uniform element in a vector space, then what we get is we can bound, so here actually we have a squared. We can bound the quantity that we want for our original polynomial by the quantities for derivatives. Some of those derivatives have no specific structure that relates to our function, but it need to come from a vector space for this to hold. And then we have this small error term that will show is small, assuming that all the Fourier coefficients are small. Okay? So I'll tell you, so I'll just prove the claim in a second. So how do we use this claim? So again, we said, so this term, we show that for a random vector space, it's bounded by the maximal Fourier coefficient, so it will be negligible.
For bounded of which dimension?
Okay, and you need the dimension to be something like log 1 over epsilon. So that's the only place where the dependence of p comes out, because the size of this vector space has to be some power of p. That's the only case where the field size comes into play. And so that will be negligible, and then what we'll choose, we'll just choose some specific vector space, and then for each one of those, we'll choose a set, and then take the union, and inductively, in the same way, it will bound the set for a original function. Okay, so that's how the proof will continue after we prove this claim.
So you're saying you can pick V to be the first the first log 1 over epsilon coordinate, the space spanned by that.
Yeah, you could do it, yeah. But then you can't guarantee that this is small. A simple way to guarantee that this is small is to choose V randomly. So V won't be axis parallel at all. It has nothing to do with the problem. So now I want to prove this claim.
So any V that has low Fourier mass,
More or less, yes.
so the F sub A, right?
Yeah, so you need the derivatives to.
Okay. That's not the AS Fourier.
No, it's not the same way. If you look on the average for a random V on that term, so it's the average of random V over the average of a random A in V of that thing, Fa hat squared. So, well, there is a chance that it's just a zero, that A is 0, right? So this is, then you're doomed. So it's at most, let's say, 1 over the size of V. And if A is not the 0, the A is just a uniform vector, and then you can just, this is just be something like bounded by F infinity squared. So that's a bound. I'll show it in a second. But essentially, then you just,
Random vector. If it's not a zero, then
yeah, exactly, it's a uniform vector, and then this is just, yeah, just a routine calculation to check it. So I think the only really new ingredient is this claim that somewhat surprised us. So let me show it, and it really will depend on this alternative way of viewing this by this coupled distribution. So somehow it will depend on that. So let me just show the proof. So first of all, so we want to bound this delta S of f. So we said we can write it as a difference of the coupled distribution minus the non-coupled distribution, or by those with that coefficient, I'll just say it's, well, I just bound it. So it's at the most, the sum where just alpha s is not is 0, but I don't insist of not taking the 0 Fourier coefficient of f hat squared. So here I'm adding this additional term of the 0 Fourier coefficient, but I don't really care because I already assume that all the Fourier coefficients are small. So it's not a major issue. And this is just the average where of choosing, right, x in f, let's do it x1 and x2 in this set ds of minus 1 f of x1 plus f of x2. Right, so that's just an equivalent way of writing it. And now the crucial part is that this set ds, this distribution, have symmetry. We can add some constant to each of those sides and it will be the same distribution. Right, so what we'll use it, if we take the distribution d of s and add to it any constant aa, we'll get again the same distribution. Right? Remember that this, how do we show this? We choose the first one uniformly, the second one we just re-randomize some elements in a set S. So we can just add a to the first element, right? So this will be the same distribution. And that will be crucial. So how do we use it? Well, we do it the following way. So now we're using Cauchy-Schwarz, so let's write ds of f squared. I want to do it the following way. So it will just be, okay, sorry. Here I want to say something else before that. So I'll just write the same thing, the same quantity, in a different way, which just be the following way. So I'll just also add here average over A in our vector space, average over x1, x2 in ds of the same thing. So it will be -1 to f of x1 plus A plus f of x2 plus A. So here we just shifted each of the inputs by a random element from our vector space. So currently doesn't seem clear why it helps us, but it does. So you can just say bound the delta SF squared. So just use Cauchy-Schwarz, we'll just use the following thing. Average over x1, x2 coming from the same distribution. And now we'll have average over A in our vector space over -1 f x1 plus A plus f of x2 plus A squared. Right? So that's just Cauchy-Schwarz. We just take some of the averages out, left some of the averages in. It's always an upper bound for a quantity. And then another way of writing is just opening the brackets here. So now we'll have A and let's say, so just use the facts that I'm using the board. And I'll just, it has to be the average of A and B, let's say. And just have the same thing but plus B. F x1 plus B plus F x2 plus B. So I just opened brackets, right? Nothing fancy. And so let's just rewrite what we have here. So let's see what we have. So we're choosing x1 and x2 coming from a distribution. Here we're adding A to both sides. Here we're adding B to both sides. But again, we said this distribution is invariant under adding any constant A to it. So we might as well, let's say, remove A and write here, instead of B, A plus B. Or maybe A minus B in general. Right? So we can again shift this distribution by A. It will be the same average. Okay, so was that clear? So we just had here plus A in each side. We just can again add A to each side. A is same. So really the way to do it, to change the direction, to replace the averages, move the average over A and B outside, have the average here over ds, and then for each A we shift it by the same A.
Do you want to write B instead of A plus B? Like
sorry. Oh yeah, sorry, yeah, that's A and B and V. So here we have it with effect, it's a vector space yet. It just could be any set. Okay, so up to now it could be any set. And then it's just A plus B. But since it's a vector space and the distribution of A plus B is the same as the distribution of just A, right? So you can just, again, remove those and remove B and just left with A and V. So again, that's the only part where we use the fact it's a vector space. The sum of two random elements is the same as the distribution of a single element.
So I guess I'm confused. You've got, oh, I see. I'm sorry.
Huh? Okay.
I was wondering why you just couldn't use the second to last quantity on the previous line.
Which one? Oh, that one?
Yeah,
No, you can't quite use it yet. This is just a shift of your function, right? It's not a low degree polynomial. But the thing is that this is already a derivative. So what do we have here? We have here, so we run, so now again we exchange the averages. Now what we have here is f of x1 plus f of x1 plus a, which is a derivative of f in direction a. Right, so this is just, if you just take that and that together, we get f derived in direction a on x1. And if you take that and that together, you get f derived in direction a and x2. So x1 and x2 are original distribution, this coupled distribution, and we evaluate them on derivatives of f in some direction. This direction is a uniform direction in the vector space. And that gives a bound, right? So we get, now the bound follows. Right? So now this is just the average over A in V. So what do we have here? We have the sum of all the Fourier coefficients, including the zero Fourier coefficient. Right? Anyway, here, so this distribution that we have here, we need to remove the uncoupled to get the sum. So, right? So this is just the average over A in V. Delta S Fa plus Fa at 0 squared. That's what I promised to get. Okay. So again, somehow I think that this small claim is somehow the heart of the proof. It's a new ingredient here. We're somehow using the fact that this distribution is on one hand coupled, but has enough symmetries to be able to somehow go use these symmetries to induct, to get derivatives. Good. So now let me just finish the proof. So we have this claim now. So let me just argue why this is small. So
Does f sub a hat of b have some nice expression in terms of Fourier? I mean, how does it relate to f hat?
okay. Right. So let's see. So no, right. It's somehow the correlation between x and x plus a. So it's not really a correlation with a linear function. It's correlated with a shift.
Oh, it's a. Oh.
Right.
I guess it doesn't have a particularly pleasant Fourier expression.
So usually it might not have, but for random A it has a very nice. Right? So if you look on the average of, let's say, a uniform vectors of -1 fa of x. So and you want to look on that. Sorry, on my mistake. Want to look for the average over fa hat 0 squared. Right, so that's what we want to bound. So I'm thinking this is a nice thing. So that's just will be, well, the average over A, and this is just be the average over x -1 fa x squared, right? That's just the definition of the zero Fourier coefficient, just the bias of the function. And again, let's open parentheses, so we'll just have x and y. So we'll just have x and y here, and that will be plus fa of y. And now we just need to open the brackets here and see what's this really. So this term is really, so we have f of x plus a plus f of x, right? That's a derivative of f in direction a, evaluated on x, plus f of y plus a plus f of y. That's a derivative of f in direction a evaluated on y. And we're choosing a uniformly, and x uniformly, and y uniformly. So what's the average of that? So if you just look on the average of -1 to that, so what do we get?
F hat to the 4.
Exactly. That's just this is just the regular linearity test, right? So this will just be, right, the sum of f, the 4 powers of the Fourier coefficient, which obviously is bounded by the maximal Fourier coefficient squared. So somehow for a random A, this acts nicely. For a specific A, it's not really related somehow to the Fourier coefficient, right? So yeah, but then, so now how do we finish? So we said for any specific vector space, then we can just approximate, you can just bound the quantities delta S of f by the averages over delta S of derivatives in this vector space plus this small error term. This small error term is really small if you choose a vector space randomly, because on average it's this term, and this term we assume is small because our function have no large Fourier coefficients. So we just choose a random v, and then just more or less similar to before, I won't do it. For each one of these derivatives, choose a set S, takes their union, and you'll get a set that bounds this delta S of f. So that somehow finishes proof.
The dimension is small enough.
Yeah, so you need the dimension to be, the dimension to be something like log 1 over epsilon. But then if the field is very large, then the size of a vector space is at least p. So if p is much more than 1 over epsilon, then you somehow you lose. Maybe if the field is very large, there's a way of choosing it not to be a vector space, not an approximate vector space, and somehow improve the parameters, but we didn't really try to pursue this. But I think there might be a way of doing it, if someone is interested in it.
Or maybe there is some relation between the different S's of the different derivatives in this vector space.
Yes, might also be. Yeah. Good. So just to conclude, so right, what we said is that, well, we have a polynomial, we want to argue by derivatives, like the usual way is argue by derivatives, that each derivative is nice, so we can just induct for the polynomial. And here we had two cases, either the polynomial have some large Fourier coefficient or not. If it had a large Fourier coefficient, everything was this more or less standard. We just approximate the polynomial as a function by some averages of derivatives, and then just induct. That was somewhat standard. The new ingredient was when it has no large Fourier coefficient, you can still somehow induct by taking random derivatives on some arbitrary vector space, and then choosing a random vector space to somehow bound the error term that we get. So I just want to finish with one open problem, and that is what is the real dependence on epsilon. So here what we get is 1 over epsilon to the 4 to the d, and but this is really not tight. So for d equal 1, really you can just choose each variable appearing in your single Fourier coefficient, because you're a linear function, and you kill all the Fourier coefficient, right? So that's easy. And for d equal 2, well, you can just choose s to be log 1 over epsilon, and that's essentially because we really understand the Fourier spectrum of quadratics. They form a vector space. So all the non-zero Fourier coefficient of a quadratic have the same value up to have the same absolute value. It's 2 to the minus the rank of the quadratic, and they form a vector space. So if you just following that, you just choose your coefficient in some greedy way, and they will guarantee it. So I don't know what is the answer for larger d's. And one thing to think why it might be interesting is because we are always killed in d, which is log n, in all of these things. Like when d reaches log n, then all these techniques die. And this also seems like it will die because we're using this Cauchy-Schwarz here. So this Cauchy-Schwarz loses a factor of square in each place. So at most, when d is log n, we'll get size n. So we can always choose all the variables, right? So we don't really have any hope there. But somehow, I don't know, maybe for this problem we can pass log n by some other means. I'm not sure. Okay, so thank you.